Hey there, YouTubers! Hi there, Dr. Sheep here. Welcome back to another chemistry video, and happy 2020! Now, I do realize that it's probably almost a month or more into 2020. However, today marks the beginning of my longest series yet on this channel. It should last for months. Today is the beginning of my series on the periodic table of elements. Today, we will talk about the different sections of the periodic table, what atoms are, what they're made out of, how and why the periodic table is organized, and finally, I will talk about the first element on the periodic table, hydrogen. Okay, so to any teachers showing this in class, I do want to mention that this may go over the heads of students 9th grade and younger. I didn't learn a lot of this stuff until I was a junior in high school, so just keep that in mind. I will not be mentioning the different models of atoms, just the modern theories and the modern model, so keep that in mind. I also will talk about electron orbitals, S, P, D, and F. So to anybody watching at home, this is a lot of information to take in at once, especially if this is your first time hearing it. So feel free to pause, rewatch, take a break. But sit back, relax, and enjoy as we explore the fundamentals of matter. Wow, the periodic table. So breathtaking. I spent way too much money on this poster. Alright, so there's some language you're going to need to understand before I move forward, and it has to do with the periodic table. Duh. Each column on the table is called a group or family. Each row is called a period. The periodic table can be split into further sections from there. I will have videos on these sections and talk about the properties of them, but for now, you will learn their names. So the first column here on the far left is called alkaline metals. Hydrogen deserves its own spot, its own section, because it has some properties of the metals below it, but also properties that don't fit there at all. For instance, it's a gas at standard atmospheric pressure and temperature, unlike the metals below it. Moving forward to the next column, you have the alkaline earth metals. This big section here is the is the transition metals, which contain some famous ones that you're probably more familiar with. Iron, cobalt, nickel, copper, zinc, gold, silver, mercury, and platinum are just some of the famous ones. Moving forward, you have this bottom part here in the periodic table. This is the rare earths. The rare earths could then be split into two rows, the lanthanides or the lanthanoids up top, and the actinides or the actinoids at the bottom. This weird staircase section here goes by multiple names, the post-transition metals, the ordinary metals, or as I'm going to call them, the staircase metals. Just remember, they are not transition metals. Moving forward, this weird section in here are called the metalloids. The metalloids have properties of metals and the properties of non-metals, so they're kind of in a weird spot. Then you have the non-metals, which is kind of this upside down staircase here. This 7th or 17th column, depending on the context, is called the halogens. And then the last section, this last column I should say, are the noble gases. Now that we have this terminology, it's time to learn about the atom. The atom is the smallest unit of matter that can be divided without the emission of charged particles. However, the atom is comprised of two sections. The outermost section is the electron cloud. The innermost section is the nucleus. The nucleus is comprised of nucleons. Okay, sorry about that. Let me use terms that are more on par with my audience. Nucleons are neutrons and protons. Protons have a charge of +1, making them positive. Neutrons have no charge. They're neutral. Remember this: positive protons and neutral neutrons. Protons are responsible for what determines what kind of atom you get. 2 protons gets you helium, possibly one of the most stable elements on the periodic table, and it's also a gas. If you add one more proton, you get lithium, an unstable element that reacts relatively violently with water and oxygen and is a solid metal. Neutrons, to put it simply, stabilize the nucleus. Each atom of a different amount of neutrons, but the same amount of protons, is called an isotope. Take uranium-238. It has a half-life of 4.5 billion years. Half-life is the amount of time it takes for half a sample to decay. This applies to any size of sample. Uranium-239, which has one more neutron, has a half-life of 23.45 minutes. Wrong direction. In the electron cloud, you will find electrons. Duh. People often say that electrons circle around the nucleus, or orbit in some cases. This isn't true. Electrons pop in and out of existence in different spots in the electron cloud. However, you can never know the exact position of the electrons. This is because of the Heisenberg uncertainty principle, which I talked about in my quantum mechanics video, which you should check out. These electrons have a charge of -1, meaning they are negative. Remember, negative electrons. Electrons are negative. Negative electrons. Atoms of the same amount of protons and neutrons, i.e., it's the same atom that has the same number of protons, whatever a different number of neutrons is, but the two atoms have the same protons and the same number of neutrons, okay, but with different numbers of electrons, are called ions. An ion has a charge either positive or negative. This is disregarding valence electrons, which we'll talk about later. Take an atom of carbon. It typically has 6 electrons. If you take one away, it becomes positive and wants to give away 3 electrons. Why does it want to give away 3 electrons? We'll talk about that later. If a carbon atom has 7 electrons, this means it wants to gain electrons and is negative. It is negative because it has more electrons than protons. If it has fewer electrons than protons, it's positive. If it has the same amount of electrons and protons, it's neutral. Kind of. Before I move forward, we have to know another piece of terminology. This terminology is valence electrons. Valence electrons refer to the electrons on the outer shell of an atom. These shells are called principal energy levels and are useful in understanding bonding and how light is created. However, they are not too important for today. You just need to understand orbitals and the octet rule. The octet rule is important in organic chemistry and refers to how many electrons an atom has in its outer shell. This relates to the stability of the atom and how willing that atom will be to bond with another atom. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. You don't have to memorize the elements. I just have it for my own fun. Electron orbitals refer to zones in the electron cloud that have a higher probability of there being electrons. These orbitals can be drawn to a point. S-class orbitals are the most simple. They're just a sphere. P-class orbitals are 2 teardrops adjacent from each other. And D and F orbitals are too complex to be shown in a 2D diagram. P-class orbitals can be on the X, Y, and Z axes. In organic chemistry, as I discussed earlier, the S and P orbitals are the key to the octet rule. If you ignore the transition and the rare earth metals, the octet rule applies to how full the S and P orbitals are, provided these are in the outer energy levels. If you combine the number of electrons in the S orbitals and the P orbitals from the same row, they would equal 8. If an atom has 8 valence electrons, it is stable. This is why the noble gases are noble. They don't bond with other elements. However, in recent discoveries, xenon has been shown to react with fluorine in the correct circumstances. If we look at lithium, it has 1 valence electron, meaning it will prefer to give that electron away. If we look at fluorine, it has 7 valence electrons, meaning it will want to steal an electron. If an atom has more than 4 valence electrons, it is most likely to steal. If an atom has less than 4 valence electrons, it will try to give those away. However, what happens at 4 electrons? Carbon is a great example because it will share those 4 with other atoms, including itself. This allows carbon to build very complex molecules. Armed with this information, we can combine it together to understand how and why the periodic table is structured the way it is. First, we need to know what everything in little boxes means. Now, every periodic table is different, but we'll focus on mine for now. The different colors of the boxes refers to what section of the periodic table that element fits in. The gray colored boxes refers to elements that their half-lives were too short to fully study the element. Ignore the color of the box in hydrogen. It deserves its own color. The number in the top left-hand corner is the atomic number. It refers to the number of protons the element has. The big letter in each box is the element symbol. The color of the symbol refers to what state of matter the element is in at standard temperature and pressure. In this case, gray is unknown. The word below the symbol is the name of the element, and the number below that is the atomic mass. This is the mass of the most stable isotope of an element, or is the average mass of an atom in nature. It's actually quite interesting how this is calculated. They take the probability of finding each isotope in the wild, and then use that to weight the average mass. Some periodic tables will have more or less information than I have just listed. Mine has more, actually. You just can't see it on the camera. It's too small. It's all listed here on every element. Whoa! I don't know how I got here, and I'm sure I've done that before, but hey, look, there's things to read. The periodic table is listed in order by atomic number, least to greatest. It was debated whether or not it should be the atomic mass. But this would reverse the order of cobalt and nickel because cobalt has a heavier atomic mass. Now the periodic table has these gaps because of d and f orbitals. The transition metals, their outermost orbitals are d's, and rare earths, their outermost are f's. The alkaline and alkaline earth metals are on the left because they have s orbitals as their outermost. The lighter elements fill their s, then their p orbitals, and don't have d's and f's. But heavier elements fill s, then d's, then f's, and then p's. Lastly, helium does not follow the octet rule, but it fills its 1s orbital, and then it also has one full energy level. So the atom is stable. Whew, finally that periodic table is gone and my crappy drawings are back. I don't think that's an improvement, and I am tired. So, finally we've discussed the basics of the atom and the periodic table. Now we start talking about the individual elements. Hydrogen has been cornered by itself because it doesn't have the same characteristics as the alkaline metals. It's a gas, and with a little extra energy, it will combust. However, theoretically, if you compressed hydrogen enough, it would turn to a metal and stay that way, even with the removal of the pressure. In this state, hydrogen is the miracle metal. It's the lightest metal possible. It can be used as a more stable fuel than gaseous hydrogen in rockets. It can be used in alloys, and it's a room temperature superconductor. This means that it can carry an electrical current with no energy loss at the speed of light. If you can make an Ethernet cable out of this, you'd have the fastest internet possible. The room temperature refers to the fact that it would work at standard pressure and temperature. Currently, all superconductors only work at temperatures well below room temperature. Hydrogen can be used in fusion reactors to generate electricity without burning fossil fuels. Our sun and all stars do the same thing. They use hydrogen to make light. It is the most abundant element in the universe. It's not the most common on Earth, but is easily manufactured. One of the most common ways of making hydrogen is through electrolysis. This is done by running an electrical current through water. The electricity breaks down the water molecules into 2 hydrogen atoms and 1 oxygen atom. The hydrogen is generated at the cathode or the negative side, and the oxygen is generated at the anode or the positive side. However, this isn't too much fun, and there are more dangerous and more fun ways to make hydrogen. Don't do this at home or anywhere. Here's a clip of me dissolving sodium hydroxide in water and then adding aluminum metal to make hydrogen. Here's a clip of me reacting lithium metal with water to make hydrogen. If you're following along at home, any alkaline metal will react with water to make hydrogen. However, the heavier alkaline metals get so warm when they are with water, they ignite the hydrogen and explode. So this is a chunk of lithium. You've seen it in my intros. When it gets dumped in water, it reacts and creates hydrogen. Oh wow. I wonder, so these are just working right away. Let's mix a little bit of soap in there. Oh boy, that's making a stink. So now, these should be hydrogen bubbles. So we have a really big thing going on here, like that. Oh, it's red! That's awesome. Here's a clip of me doing an experiment that I haven't done since middle school. I react magnesium with vinegar to make hydrogen. This experiment is magnesium and vinegar. I haven't done this experiment since I was in 7th or 8th grade. So what I have here is a piece of magnesium ribbon, and this is vinegar. So the magnesium will start to dissolve into the vinegar, effectively, which will release hydrogen as it breaks. You'll just watch. And I don't believe that's hydrogen. If you hear that little popping. Finally! The end of the video. Honestly, I have no idea how this turned out. The electron orbitals made me so confused, I had to reteach myself basically everything. Anyways, I'll see you in 2 weeks to talk about the alkaline metals. In the meantime, I'd like to thank you all for watching. Please like, comment, share, and subscribe. New videos every other Friday, 2 p.m. Central Time, and good night. Subs for trees, subs for trees, subs for trees, subs for trees. Oh, you're still here? I thought I told you to go home. Oh, you want more? I'm flattered. Check out the playlist. If you want exclusive content, check out my Instagram, Dr_sheep_YouTube. That's all lowercase. If you want to help the earth, subscribe. When I reach 100 subscribers, I'm going to plant 10 trees. If you feel that's too small, then check out my channel chart where I lay out even bigger goals. Finally, stick around for the next 20 seconds to give me that sweet watch time. Bye.